When you stand on the earth, doing nothing at all, not walking, not jumping, not trying to lift anything heavy, there is one feeling so familiar that you almost never stop to question it. Weight. Your feet press into the floor. Your knees carry you. Your spine makes tiny corrections. And somewhere in the background, your muscles keep making small adjustments just to keep you upright. It all feels obvious. Almost too obvious. The earth pulls me down. I feel heavy. Therefore, what I am feeling must be gravity. That is the ordinary answer. And it sounds perfectly reasonable. But physics often becomes interesting at exactly the point where common sense says, "Stop looking. This part is already settled." Because the strange thing is this: when you feel your own weight, you are not directly feeling gravity itself. You are feeling the world stopping you from falling freely. Now pause on that for a second. Because at first it sounds wrong. Your body almost wants to argue with it. If you are standing right now, you can feel something in your feet, maybe in your knees, maybe in your lower back. If you stand long enough, your body makes it very clear that standing is not nothing. So the feeling is real. The heaviness is real. The tiredness in your muscles is real. The question is not whether you feel something. Of course you do. The question is more precise. What exactly is your body reporting? Is it detecting gravity directly? Like some little gravity sensor hidden in your bones? Or is it detecting pressure, compression, support, the push of the floor against your feet because gravity is trying to carry you downward? That may sound like a tiny distinction, but it is not tiny at all. It is the difference between the motion gravity would give you and the force that stops that motion from happening. Try it without equations first. That is usually the cleanest way in. Do not imagine a diagram yet. Do not draw arrows. Do not rush to formulas. Just imagine your own body standing barefoot on a solid floor. Your skin touches the surface. Your bones stack upward. Your muscles keep the structure from tipping over. And beneath you is the earth. Massive. Quiet. Pulling everything toward it. Gravity is absolutely there. There is no trick in that part. The earth has mass. You have mass. And because of that relationship, your body is drawn toward the earth. If the floor vanished beneath you, you would not politely remain suspended in mid-air. You would fall. Near the surface of the earth, your downward speed would increase by about 9.8 meters per second every second. But do not let that number become decoration. It is not there just to sound scientific. It says something simple and physical. If nothing blocks you, gravity keeps changing your motion. But now look at what is happening when you stand still. You are not gaining downward speed. You are not sinking through the room. You are not passing through the wood, the concrete, or the tile beneath your feet. So something must be interrupting the motion gravity would otherwise give you. That something is the floor. And the floor is not just scenery. It is not a passive stage where gravity performs the real drama. At a microscopic level, your feet are made of atoms. The floor is made of atoms. And when those atoms are pushed too close together, electromagnetic forces resist that compression. Matter does not simply let other matter pass through it. So the floor pushes upward on you. Not poetically, not symbolically, literally. The floor is pushing back. And once you notice that, the ordinary feeling starts to look different. When you stand, the pressure is mostly in your feet. When you sit, it moves into your hips, your thighs, your back. When you lean against the wall, the pressure shifts into your shoulder or your side. That little observation matters. Because the feeling follows contact. It follows the places where the world presses on you. If weight were simply your body feeling gravity as an invisible pull spread evenly through every atom, then you might expect the sensation to be everywhere in the same way. But that is not how it feels. Your nerves report local things. Skin pressure, muscle tension, joint compression, bones carrying load. The body is not giving you a clean announcement that says, gravitational field detected. It is saying something much more practical. Something is pressing here. Something is supporting me here. Something is stopping motion here. That is the first reversal. And it is worth sitting with for a moment. Gravity is trying to give your body a falling motion. The ground blocks that motion. And your nervous system gives the conflict a familiar name. Heavy. At first, that sounds like a small correction. But it changes the meaning of weight completely. Weight is not simply the feeling of being pulled downward. It is the feeling of being prevented from moving the way gravity would let you move if nothing stood in the way. Your body is caught between two physical facts. The earth pulls. The floor resists. And that little argument travels through your feet, your bones, your muscles, your skin, until your brain turns it into one simple sentence. I feel heavy. Now remove the floor. Only as a thought experiment, not as a dangerous suggestion. Imagine you step off a ledge, or imagine the floor beneath you simply disappears. Leave fear out of it for a moment, because we are trying to isolate one physical idea. Gravity has not turned off. In fact, gravity is now acting more freely than before. There is no floor pressing into your feet, no chair supporting your back, no surface squeezing your skeleton upward from below. Your whole body begins to fall together. Your head, your feet, your stomach, your arms. All of it shares almost the same motion. And because every part of you is being carried along together, the usual support pressure fades. The pressure in your soles disappears. The compression in your legs disappears. And the feeling you normally call weight begins to vanish. This is why free fall feels so strange. Not because gravity has disappeared, but because the thing you usually mistake for gravity has disappeared. The body does not have a simple alarm that says, gravity is present. It is more practical than that. It notices pressure, stretching, bending, squeezing, contact. It notices when one part of you is being pushed differently from another part. But in clean free fall, when the whole body is allowed to move almost as one system, there is much less internal stress to report. The body becomes strangely quiet. Gravity is still changing your motion, but the familiar message of heaviness is gone. You can see the same idea in orbit. And this is where many people get fooled. They imagine astronauts floating because space is a place where gravity has vanished. But that is not what is happening. The International Space Station is not outside Earth's gravity in any simple sense. Earth still pulls on the station, and Earth still pulls on the astronauts inside it. The difference is that the station and the astronauts are falling together around Earth. They share the same motion. The floor of the station does not have to hold them up the way your floor holds you up right now. Their feet are not being pressed hard into a surface. Their chairs are not carrying their bodies in the ordinary way. Their muscles are not receiving the usual message of support from below. So they float. Not because gravity is absent, but because the support force is absent. Gravity remains. The sensation we usually blame on gravity disappears. You do not need a spacecraft to feel a small version of this. Think about an elevator. When the elevator starts moving upward, there is that brief heavy feeling. Your feet press harder into the floor, and for a moment, it feels as if your body has gained weight. But the Earth did not suddenly become more massive. Gravity did not become stronger because an elevator motor switched on. What changed was the push from the floor. The elevator floor had to push harder on you to accelerate you upward. And your body read that stronger push as extra heaviness. Then when the elevator begins moving downward, you feel slightly lighter. The floor presses less strongly into your feet. And for a second, your body gets a tiny preview of release. Almost a small hint of free fall. Now imagine the elevator falling freely. Again, leave aside the danger, because the point is not the accident. The point is the physics. If you and the elevator accelerate downward together, then the floor no longer has to press hard into your feet. You would float relative to the elevator. Not because Earth stopped pulling you, but because nothing inside the elevator is holding you up against that pull. That is the key. Your body does not say, "I am inside a gravitational field." It says something simpler. Something is pushing me. Something is squeezing me. Something is supporting me. Take away that support, and the feeling changes completely. This is the part that quietly turns ordinary intuition upside down. Standing still feels normal. Falling feels abnormal. But from the point of view of gravity, falling is the natural motion. Standing still is the interrupted motion. That sounds strange because we live on floors, chairs, roads, beds, surfaces. We spend our lives being supported. So support feels like the default state. But physically, when you stand on Earth, you are being pushed away from the path you would naturally follow if nothing blocked you. Compared with a freely falling object beside you, the ground is constantly forcing you away from that falling path. That upward push is what your body reads as weight. Standing still is not as simple as it looks. It is a continuous correction. Now we have to be careful here, because this idea can easily be misunderstood. It does not mean gravity is imaginary. It does not mean gravity is weak, fake, or only psychological. Gravity is completely real. It shapes the fall of a stone, the orbit of the moon, the path of Earth around the sun, and the motion of every object you have ever dropped from your hand. The point is more subtle. Your body does not sense gravity the way it senses a hand pressing against your skin. A hand creates local pressure. Your nerves detect that pressure, and you feel contact. Gravity is different. If gravity accelerates every part of you almost together, then there may be no strong internal pressure announcing what is happening. The motion is real, but the sensation is indirect. That makes the body a fascinating instrument. It is wonderfully sensitive to some things, and almost blind to others. It notices the floor under your feet. It notices a seat pushing into your back. It notices when muscles stretch, when skin compresses, when balance shifts. But it does not simply announce the existence of a gravitational field by itself. The body asks local questions. Am I being pushed? Am I being squeezed? Am I being stretched? Am I being stopped? When you stand on Earth, the answer is yes. The floor is stopping you from falling, and that is why you feel weight. In free fall, that answer becomes almost no, and the feeling of weight fades away. There is one exception that makes the idea even clearer. If gravity does not pull equally on every part of your body, then you can feel the difference. These are tidal effects. Near Earth, in ordinary life, the difference between the pull on your head and the pull on your feet is far too small for your body to notice. But near something extreme, like a black hole, that difference could become enormous. One part of your body could be pulled much more strongly than another part, and then your body would stretch. But notice what you would feel even there. You would not feel gravity as a pure invisible idea. You would feel stress inside the body. You would feel different parts of you being forced into different motions, and your tissues would report that difference as tension, stretching, pain. So even the exception teaches the same lesson. What you feel is not gravity, as a simple invisible pull. You feel differences, pressure, distortion, contact, compression. You feel what happens when your body is not allowed to move smoothly as one system. If every part of you falls together, there is surprisingly little to feel. But if one part is pushed, or held back, or stretched more than another part, your body notices immediately. That is why weight is such a convincing illusion. It feels like gravity, because gravity is the reason support is needed. But the sensation itself comes from the support. This simple observation became one of the deep clues that helped Einstein rethink gravity. Newton had already given us an astonishingly powerful way to calculate gravitational motion. Falling objects, projectiles, planets, tides, orbits. All of these could be described with extraordinary success. But Einstein noticed something hiding inside ordinary experience. A person in free fall does not feel weight, and a person inside a sealed box accelerating through empty space could feel something just like weight. Imagine that box far from any planet. If it accelerates upward, the floor pushes against your feet. You feel heavy. But there may be no earth beneath you at all. From inside the box, if you cannot look outside, the feeling can be indistinguishable from standing on a planet. That is not just a clever puzzle. It is a clue about how nature is organized. The feeling of weight can come from gravity plus support, or from acceleration without a planet. In both cases, your body is not identifying the deeper cause directly. It is identifying pressure. It is identifying the floor pushing into your feet. The body does not say, "This pressure comes from Earth, and this pressure comes from a rocket engine." It only says, I am being supported. I am being compressed. I am being forced away from free motion. That is why acceleration and gravity are so deeply connected in Einstein's thinking. The ordinary sensation of weight is not ordinary at all. It is a clue hidden inside your own body. So the next time you stand still, try a small experiment in your mind. Do not picture gravity as a giant hand pressing down from above. Picture something simpler and more precise. Gravity is trying to carry your body into free fall. The ground does not allow it. The floor pushes upward. Your tissues compress slightly. Your muscles adjust. Your bones carry the load. And from those local pressures comes the familiar feeling of weight. You are not feeling gravity speak directly. You are feeling matter answer gravity on your behalf. The earth says, fall. The floor says, not through here. And your body feels the result. That is why the statement matters. You do not feel gravity directly. You feel the forces that prevent you from freely following gravity. You feel the ground, the chair, the elevator floor, the rocket seat. You feel contact forces, support forces, constraints. And once you see that, the ordinary world becomes a little less ordinary. Standing still is no longer just standing still. Sitting in a chair is no longer completely passive. Every moment of weight is evidence that your motion is being constrained. Earth is drawing you into a fall, and the matter beneath you is quietly stopping that fall from becoming motion. And maybe this is why we are fooled so easily. We are creatures of contact. We understand floors, walls, chairs, pressure, balance, pain. We are not naturally built to feel fields directly. We feel what fields make the surrounding world do to us. Gravity shapes the motion, but the floor gives your nerves something to report. Gravity gives the falling tendency. Matter blocks the path. And the pressure created by that blocking is what you call weight. So the next time your feet press against the ground, do not treat the feeling as ordinary too quickly. The most familiar sensation in your body is not simply gravity acting on you. It is the feeling of being prevented from following gravity freely. It is the quiet physical fact that even standing still is not nothing. It is gravity trying to give you a path, and the ground beneath you answering, not yet. So, let us take the idea one step further. But this time, let us be very careful about what we are actually saying. Because the phrase, "I feel gravity," sounds obvious, almost too obvious. You stand on the ground, you feel heavy, and gravity is pulling you downward. So the mind connects those two things immediately. Gravity is there. Weight is there. Therefore, I must be feeling gravity. But physics has a way of making ordinary sentences a little dangerous. Not because the words are foolish, but because they hide the mechanism. The first question is not really, "Do you feel gravity?" The first question is, what does it mean to feel anything at all? And I do not mean that philosophically. I mean it physically. Your body does not have a little instrument inside it that says, "Ah, yes, a gravitational field is present." That is not how sensation works. Your body feels deformation, pressure, stretching, compression, strain. It feels one part of you being pushed differently from another part. It feels tissues being squeezed, nerves being stimulated, organs shifting slightly under support. That is the language your body understands. Not pure force in the abstract, but force that creates internal difference. Stand on the floor for a moment, and do not think of this as an equation yet. Think of it as a very ordinary physical situation. Your feet want to follow the motion gravity would give them, but the floor refuses. The atoms in the floor push against the atoms in your feet. That push begins at the soles, then travels upward through your ankles, your knees, your hips, your spine. Your body is not being supported all at once in some magical uniform way. It is being held up from below. And because of that, your lower parts carry more direct compression than your upper parts. Your feet are squeezed first. Your legs carry the load. Your torso stacks above them, and your internal organs settle into that supported structure. That is what you call weight. Not gravity by itself, but the stress created because the ground is stopping you from doing what gravity alone would make you do. This is the little reversal that matters. The thing you feel when you stand still is not the freedom of gravity acting on you. It is the resistance against that freedom. It is the floor saying no, and your body reporting that no as pressure, compression, heaviness. Now remove the floor. Not in some dramatic way, just in the cleanest thought experiment possible. Imagine that support disappears. Your feet are no longer being stopped before the rest of you. Your head is no longer being held in a different condition from your stomach. Your spine is no longer carrying a stack of weight above it. Everything begins to fall together. And that word together is doing almost all the work. Your feet fall. Your knees fall. Your chest falls. Your brain falls. The tiny fluids inside your inner ear fall. Gravity has not gone away, but the differences inside your body have almost disappeared. And without those internal differences, what is there for the body to report? There is no floor squeezing your feet, no spine carrying the same load in the same way, no normal pressure chain rising from the ground. You are still under gravity, but you are no longer being held against gravity. So the sensation changes completely. You feel weightless, not because gravity has stopped acting, but because your body has stopped being internally distorted by support. That is free fall. And free fall is often misunderstood because the word sounds like absence. We say weightless, and the mind quietly hears gravityless. But those are not the same thing. Weightless does not mean no gravity. It means no support force creating internal stress. If you are falling freely near Earth, gravity is still acting strongly. In fact, gravity is exactly why you are falling. But since every part of you is being accelerated together, your body has no ordinary way to feel that acceleration as weight. This is where the elevator example becomes useful. Not because elevators are mysterious, but because they let you feel the physics in your stomach. Stand inside an elevator at rest, and the floor pushes upward on your feet with the usual strength. You feel normal. You do not even notice it, because normal weight is the background noise of your life. Now imagine the elevator begins accelerating upward. For a moment, the floor has to push harder on you. Your feet press harder into the floor. Your legs stiffen slightly. Your body feels more compressed. You feel heavier. But gravity did not suddenly become stronger. What changed was the force of the floor, the constraint, the push that distorts your body from below. Now let the elevator accelerate downward. And you know the feeling immediately. That small drop in the stomach, that strange lightness, that half second where your body seems less attached to itself. The floor is still there, but it is pushing less strongly. The internal compression decreases. You feel lighter. And if the elevator could fall downward at exactly the same rate as gravity, then the floor would no longer need to push on you at all. Your feet would not press into it. Your body would not be stacked against it, and you would float inside the elevator. Gravity would still be there, but weight would vanish. So the rule is not you feel gravity when gravity is present. The rule is stranger and more precise. You feel the departure from free fall. Whenever something prevents you from following the path, gravity naturally gives you. Internal forces appear. And those internal forces are what you call weight. Standing on Earth feels normal only because the ground is constantly stopping your natural fall. Every second you stand still, you are being prevented from moving along the path gravity would otherwise give you. The floor is doing work in the language of constraint. Not necessarily energy work, in the simple everyday sense, but physical enforcement. It is forcing your body away from freefall. That is why standing still is not as simple as it looks. We usually think falling is the dramatic condition, and standing is the calm one. Emotionally, that makes sense. Falling is frightening. Standing is ordinary. But physically, the story is almost reversed. In a gravitational field, free fall is the natural motion. Standing still requires continuous interruption. It requires the earth beneath you to push upward on you every moment. It requires your body to transmit that push through bones, muscles, tissues, and nerves. That transmitted stress is what you feel as being heavy. Now, imagine a spacecraft far away from planets, far enough that we can ignore gravity for the moment. You float inside it, no floor pressing under your feet. No up, no down, no ordinary weight. Then the spacecraft fires its engines and begins accelerating in one direction. Suddenly, the back wall of the spacecraft catches you. It presses into your feet, or your back, depending on how you are oriented. Your body is compressed again. Your nerves report pressure again. And if the acceleration is just right, the sensation can feel exactly like standing on a planet. That is a very important clue. Because in one case, you feel heavy while standing on Earth. In another case, you feel heavy inside a rocket accelerating through empty space. The causes look different from the outside, but the body does not care about the outside story. The body cares about the local stress. It cares whether your feet are being pushed, whether your tissues are compressed, whether one part of you is being forced differently from another part. If the internal pattern is the same, the sensation is the same. This is why the equivalence between gravity and acceleration is not just a clever statement from a textbook. It is something your body almost understands before your mind does. An accelerating spacecraft can imitate weight, because weight is not the pure presence of gravity. Weight is the body's response to being forced away from its natural motion. On Earth, the ground does that forcing. In a rocket, The accelerating floor does it. Different causes. Same internal stress. Same sensation. So when we return to the question, why can you not feel gravity? The answer is no longer mystical. You cannot feel gravity directly because gravity does not normally grab one part of your body and leave another part behind in a way your senses can easily detect. It gives your whole body nearly the same acceleration. Your head, your feet, your hands, your stomach, all follow together. And if all parts move together, there is very little internal squeezing caused by gravity itself. No strong internal stress. No strong nerve signal. No direct feeling of gravity. What you feel instead is interruption. You feel the chair holding you up, the floor pushing back, the elevator changing acceleration, the rocket wall pressing into you. You feel contact forces. You feel constraints. You feel the mechanical argument between your body and whatever is preventing it from moving freely. Gravity sets the stage. But the stage floor is what you feel under your feet. And this gives us a cleaner way to say it. The absence of feeling is not the absence of gravity. It is the absence of differential stress inside the body. A force can be very real and still leave no ordinary sensation if it acts too uniformly across you. What matters to sensation is not simply whether something exists, but whether it creates a detectable difference within the system that is trying to feel it. Your body is not built to detect every physical field directly. It is built to detect changes, gradients, pressures, distortions. That is why this whole subject feels backwards at first. The thing we call weight is not the simplest evidence of gravity. It is evidence that something is preventing free fall. The more strongly that prevention happens, the heavier you feel. The less strongly it happens, the lighter you feel. Remove it completely, and you float. Even though gravity may still be guiding your motion with complete authority. But there is one more step, and it is the step that makes the whole picture deeper. So far, we have spoken as if gravity is a force pulling you downward. That is a useful way to begin, especially when we are talking about floors, elevators, and falling objects. But it is not the final way physics describes gravity. In the deeper description, gravity is not treated as an ordinary force in the same sense as a push from the floor or a pull from a rope. It becomes part of the structure of space-time itself. And if that sounds abstract, keep the simple picture in mind. In free fall, you are not fighting anything. You are following the natural path available to you. You do not need to feel a force because locally, in that falling frame, your body is not being forced out of its natural motion. The ground is what feels like a force because the ground prevents that path. The floor interrupts the motion your body would otherwise take. So, the strange conclusion begins to make sense. Falling freely is not the strange case. Standing still is. That is the point where gravity stops feeling like a simple downward pull and starts looking like geometry. Matter tells motion what paths are natural, and objects follow those paths unless something pushes them away. Your body does not feel the path itself. It feels the push that knocks it away from that path. A floor, a chair, a rocket, an elevator. These are the things that create the internal stress your nerves can report. So the next time you stand quietly on the ground, the ordinary feeling of weight should look a little less ordinary. You are not simply feeling gravity. You are feeling the earth preventing you from falling. You are feeling the upward push of matter beneath you. You are feeling compression traveling through your own structure. Gravity is there. Absolutely. But the sensation comes from the resistance, from the constraint, from the fact that your natural path has been blocked. And that is why you can live your whole life inside Earth's gravitational field, surrounded by it every second, shaped by it in every movement, and still never feel gravity directly in the simple way you imagine. What you feel is not the invisible field itself. You feel what happens when something stops you from obeying it. Gravity acts continuously, silently, everywhere through your body. But your body only speaks when there is stress, when one part presses against another, when support appears, when free fall is interrupted. So the mystery dissolves. Not because gravity is weak, and not because it is absent, but because gravity, when it carries you and every part of you together, leaves almost nothing inside you to complain about. The complaint begins when the floor gets involved. And that complaint, that pressure, that compression, that ordinary feeling of being heavy, is what we have been calling weight all along. When we say gravity is a force, it sounds simple. Maybe too simple. You drop a stone, and it falls. You jump into the air, and the earth brings you back. A cup slips from the edge of a table, and before it even reaches the floor, your mind has already finished the story. Of course it goes down. That is the picture most of us grow up with. Gravity pulls things. It pulls stones. It pulls rain. It pulls the moon. It pulls your body toward the ground. And if gravity is pulling you right now, while you are sitting there, standing there, breathing without thinking about it, then the obvious question is this: why do you not feel it directly? Now pause there. Because that little word, feel, is more dangerous than it looks. What would it actually mean to feel gravity? Not to know about gravity, not to calculate it, not to see its effects, but to feel it inside your body. If gravity is acting on your head, your chest, your stomach, your blood, your bones, every little part of you, then why does your body not send some clear message saying, yes, something is pulling me downward? It is a strange question, almost childish. But I like childish questions in physics. They often point to the one thing everybody has stopped noticing. Think about where you are right now. If you are sitting in a chair, you might say, I feel my weight. And in everyday language, that is fine. But look a little closer. Shift your body slightly in the chair. Lean to one side. Press your feet into the floor. Relax your shoulders for a moment. What changed? Gravity did not suddenly become stronger. Earth did not pull harder for half a second. What changed was pressure. The pressure under your legs. The pressure on your back. The pressure where your feet meet the floor. That is the first clue. Your nerves are not reporting gravity as a mysterious, invisible touch. They are reporting contact, pressure, compression, Support. Something is pushing on me. Something is holding me up. Something is stopping my body from moving the way it otherwise would. That difference is small in language, but enormous in physics. Because here is the part that feels backwards at first. When gravity has you most completely, when nothing is holding you up, when the floor disappears beneath you, that is exactly when you feel weightless. Not a little lighter, not gently held by some invisible hand. Weightless. Imagine the first instant of a falling elevator. I do not mean the danger of it, just the physics of that first instant. Your stomach jumps. But not because gravity suddenly appeared. Gravity was already there. The strange feeling comes because the support vanished. Your body expected the floor to keep pushing back, and for a moment, that push is gone. Now imagine the fall continuing. You are falling. Your blood is falling. The air around you is falling. The coins in your pocket are falling. A pen floating beside you is falling too. Everything is going together. And because everything is going together, there is no strong squeeze inside you. No obvious internal signal that says, I am being pulled down. Your body is not really a gravity detector. It is more like a stress detector. It notices pressure under your feet, tension in your muscles, strain in your bones. It notices when one part of you is being pushed differently from another part. But if every part of you moves together, almost equally, almost quietly, then there is very little for the body to complain about. No alarm bell, no felt rope, no little voice inside saying, gravity is touching me now. This is where the word force can mislead us. The word makes us imagine something familiar. A hand, a rope, a magnet. Something reaches out, grabs, pulls. And to be fair, that picture is not stupid. Newton used it with astonishing success. If you want to calculate falling stones, cannonballs, planets, orbits, Newton's picture is one of the most powerful tools human beings have ever made. But this question is a little different. We are not only asking, how does an object move? We are asking, why does my own body not feel gravity directly? And for that question, we have to slow down. Einstein had a beautifully simple way into this problem. Imagine you are inside a sealed box. No windows. No stars outside. No earth visible below you. Just you. A floor. And a few objects in the room. In one case, the box is sitting on a planet. Your feet press into the floor. You drop a small object, and it falls. Your legs feel loaded. Your muscles carry your posture. Everything feels normal. Now take the same box. Put it far out in empty space. No planet nearby. No obvious gravity around it. But attach rockets underneath it, and let those rockets accelerate the box upward. What would you feel inside? Your feet would press against the floor. You would drop a small object, and the floor would rise up to meet it. Your legs would feel loaded. Your muscles would feel weight. And if you had no way to look outside, your body would not know which story was true. A planet below you, or a rocket behind you. Gravity, or acceleration, Your nerves do not receive a neat label saying, "This pressure came from Earth," and "that pressure came from a rocket." Your body only knows the local situation. Feet against floor, bones carrying load, muscles holding shape. That box story may sound like a trick, but it is really a warning. Your body is not a perfect instrument measuring the universe from the outside. It is doing something simpler and more practical. It asks, where is the pressure? Where is the strain? What is pushing against me right now? Once you see that, gravity begins to look less like an invisible hand. If gravity can be present while you feel weightless in freefall, and if the feeling of weight can be copied by acceleration in a sealed box, then maybe gravity is not the same kind of force as a hand pushing your shoulder or a rope pulling your arm. Maybe gravity is telling us something deeper about motion itself. So let us rebuild the picture carefully. Imagine an object far from planets, far from stars, drifting through empty space. If nothing pushes it, it does not need help to keep moving. It simply continues, straight ahead, at constant speed. That sounds plain because it is plain. An object does not need a force to keep moving. It needs a force only to change its motion. Now bring Earth into the story. Suddenly the paths of objects look different. A stone does not follow the straight line your eyes expected. It curves downward. A satellite does not simply fly away forever. It keeps bending around the planet. Newton gives us a very useful way to say this. Earth pulls them. And that works beautifully for calculation. But Einstein asked the question from another angle. What if the object is not being dragged away from its natural path? What if it is following its natural path, but near Earth? Natural path does not look like a simple straight line anymore. That is where space and time enter the story. Not as decoration, not as mystery words, but as the stage on which motion happens. Mass and energy change that stage. They change what counts as the straightest possible path. So near a massive body, an object can be doing the simplest thing available to it, and still look to us as if it is curving. The stone is not struggling. It is not squeezing itself downward. It is not firing some little engine toward the ground. It is following the path that space-time gives it. Physicists call such paths geodesics. The word sounds fancy, but the idea is not meant to be fancy. It is just the closest thing to a straight line when the geometry itself is curved. You already know something a little like this. Think of a flight path between two faraway cities. On a flat map, the route may look curved. But on the globe, that same route can be the natural shortest path. The map makes it look bent because the map is not the real geometry. Free fall is similar in spirit. From one point of view, it looks like forced motion. From a deeper point of view, it is natural motion through curved spacetime. Now bring this back to your body. Suppose you step off a platform, or imagine an elevator whose cable has been cut. For the moment, ignore air resistance. Not because air is unimportant in real life, but because we want to see the clean idea first. During the fall, your head, your stomach, your legs, your blood, all follow almost the same natural path. Your feet are no longer being pushed upward by the floor. Your skeleton is no longer carrying your body from below. Your muscles no longer feel the same compression they feel when you stand. So your body gives a simple report: weightless. This is the reversal that takes a moment to accept. Standing still feels like rest. Falling feels like motion. Falling feels dangerous because near Earth, it usually ends with an impact. But physics is asking a cleaner question. What is being forced? In general relativity, free fall is closer to natural motion than standing still is. When you fall freely, you are going along with the geometry. When you stand on the ground, your natural path would continue downward. And the ground refuses to let that happen. That refusal is what your body calls weight. Try to feel it right now. Press your palm gently against the desk. You are not feeling some invisible planetary hand inside your palm. You are feeling resistance. Your hand pushes. The desk pushes back. The same kind of thing happens under your feet every time you stand. The atoms in the ground push against the atoms in your feet. Your feet push into your legs. Your legs push into your hips. Your skeleton carries the load. Your muscles keep the structure balanced. Your nerves report all that pressure and compression. And your mind gives the whole experience one simple name: weight. So, the everyday sentence is a little misleading. We usually say, I feel gravity because I am standing on Earth. But more carefully, you feel the Earth stopping you from following the path gravity would let you take. That is why astronauts float. Not because gravity has vanished, but because they and their spacecraft are falling together. Continuously. Around Earth. Missing the ground again and again. The phrase zero gravity is convenient. But it can fool us. An astronaut in orbit is not floating because Earth has let go. Earth has not let go. Earth is still bending the spacecraft's path. The difference is that the astronaut, the camera, the air, the loose screw drifting near the wall, are all sharing the same fall. And when everything falls together, nothing inside has much reason to press hard against anything else. No floor pushes the astronaut's feet upward. No chair carries the body from below. No skeleton takes the same kind of load it takes on Earth. That is what the body experiences as weightlessness. Not the disappearance of gravity, but the disappearance of the support force your body normally feels. But we should be careful here. Gravity is not always perfectly smooth. If every part of your body were accelerated in exactly the same way, there would be no internal stretching, no squeezing, no clear signal. But real gravitational fields can change from place to place. Your head is slightly farther from Earth than your feet. That means one part of your body is not in exactly the same gravitational situation as another part. Near Earth. Across the height of a human body. That difference is tiny. Far too small for you to notice. But the principle matters. These differences are called tidal effects. This is where gravity can become something the body really would feel. If your feet are pulled a little more strongly than your head, your body is stretched. If the field squeezes from the sides, your body is compressed. Now, gravity is not acting like one smooth shared motion across the whole body. It varies from one part of you to another. And variation is something your body can notice. So the key is not just gravity. The key is difference, unevenness, stress. Your body does not feel gravity simply because gravity exists. It feels pressure, constraint, compression, stretching. You feel the floor blocking your fall. You might feel tidal stretching near something extremely compact and massive. But smooth free fall, when all parts of you move together, gives the body almost nothing to report. Near Earth. That is why the situation feels so ordinary. The gravitational field across your body is almost uniform. The difference between what happens to your head and what happens to your feet is very small. If you were falling freely, with air resistance ignored, you would feel weightless. Not because Earth stopped attracting you, but because Earth would be accelerating almost every part of you together. No large tearing, no strong squeezing, no pressure from the floor, no signal your nerves can translate into weight. Near a black hole, or near any object where gravity changes violently over a short distance, the story becomes very different. Then the difference between your head and your feet can become enormous. One part of your body tries to follow one path, another part tries to follow another, and your body is caught between them. That is no longer peaceful weightlessness. That is stress, stretching, compression, and if the difference is strong enough, destruction. So come back to the original question. Why can you not feel gravity directly? The answer is not that gravity is absent, and it is not that your body is somehow failing. Your body is doing exactly what it is built to do. It detects stress. It detects pressure, tension, compression, stretching. But smooth gravity can move the whole body together, almost silently. And when the whole body follows that motion together, there is no internal complaint. That is the quiet trick. Gravity does not have to announce itself like a shove. It does not press on your skin like wind. It does not pull on your bones like a rope. It changes the path your body naturally follows. And if you move along that path freely, you may feel nothing at all. Standing on the ground is therefore not as simple as it feels. It feels normal only because you have lived with it since birth. But physically, it is a state of interruption. The ground is constantly preventing you from following the path you would otherwise take. Your body carries that interruption as weight. Free fall feels strange because we fear it, and because near Earth, it usually has consequences. But in the clean language of physics, free fall is the less forced state. It is the state where your body is no longer being held away from its natural motion. Once that clicks, familiar things begin to look different. An orbit is not a spacecraft escaping gravity. It is a spacecraft falling in just the right way. Weightlessness is not gravity disappearing. It is shared free fall. The heaviness you feel in your chair is not gravity grabbing you like a hand. It is the chair interrupting the fall your body would otherwise follow through curved space-time. The floor beneath you is not merely supporting you. It is saying no to the path your body would otherwise take. And that is why this little question is so powerful. It begins with something ordinary. A person standing on Earth, feeling weight, wondering why gravity itself cannot be felt. But if you follow the question carefully, it changes the meaning of motion. Gravity is not simply a downward pull hiding inside daily life. It is part of the shape of the stage. It tells matter how to move when nothing else interferes. And the thing you call weight, The thing you feel when your feet touch the floor in the morning is not gravity speaking directly through your nerves. It is the floor answering on gravity's behalf. So the next time you stand still, do not trust the stillness too quickly. Your body is being held away from the path it would naturally take. The atoms beneath you are pushing back. Your bones are carrying that push. Your nerves are reporting the stress. And your mind gives the whole experience one simple name: weight. But gravity itself remains strangely quiet. Not because it is absent, but because it is deeper than the kind of contact force your body was built to feel. That is the reversal. You do not feel gravity directly when you fall, because falling is not the interruption. Standing is. You do not feel gravity directly, because gravity is not pressing through your body like a hand or a floor. It is shaping the route your body naturally follows. You feel weight when something stops that route, or when gravity changes so sharply from one part of you to another that your body is stretched or squeezed. So gravity is everywhere in the story, but almost never in the way intuition first imagines. It guides planets, bends orbits, shapes the motion of spacecraft, and defines the fall of every object near Earth. Yet, inside a freely falling body, there may be silence. No pressure, no strain, no felt pull. Just motion following geometry. And from here, the idea opens outward. If falling is natural motion, then orbiting is not an exception to falling. It is falling stretched around a world. A spacecraft floats not because gravity has disappeared, but because everything inside it shares the same fall. The moon moves not because it has escaped Earth completely, but because its forward motion and Earth's gravity combine into one continuous curved path. Whole systems can move under gravity without feeling gravity, because feeling requires stress, not merely motion. That is where the next step begins. Not with one person standing on Earth, but with bodies in orbit, spacecraft in freefall, moons circling planets, and planets tracing paths around stars. Once you understand that gravity is not always something you feel, but something that shapes the natural motion of everything, the universe stops looking like a collection of objects being pulled by invisible strings, and starts to look like matter moving through a geometry it cannot help but obey. We are going to make the picture a little bigger now, but I do not want to make it heavier than it needs to be, because the whole idea still fits in your hand. If nothing is stopping you from falling, you do not feel gravity as weight. You feel the thing that gets in the way. The floor, the chair, the ground under your feet. That is the strange little clue. And once you notice it, you can carry it all the way upward. Above the trees, above the clouds, above the thick air of Earth, to a place where people float and everyone says, "Look, gravity must be gone." But let us slow down there, because that sentence sounds right only because we have heard it too many times. Think about a spacecraft circling the Earth. The International Space Station, for example. From the ground it looks like a machine racing around the planet at a ridiculous speed. But inside, the scene is almost quiet. A pencil drifts near an astronaut's hand. A drop of water hangs there like a tiny glass planet. A person gives the wall a gentle push and slowly crosses the room. Nothing falls to the floor. Not because gravity forgot about the room, but because the room itself is falling too. That is the first place where our everyday intuition gets fooled. We see floating, and we think absence. No weight must mean no gravity. But at the height of the space station, gravity is still strong. It is weaker than it is down here on the surface. Yes, but not weak enough to ignore. It is strong enough to keep pulling that whole station into a curved path again and again and again. So the real question is sharper than people usually make it. If gravity is still there, why does the astronaut not feel heavy? Here is the trick. And it is beautifully simple, once you let it sit for a moment. The station is falling. The astronauts are falling. The pencil is falling. The water drop is falling. Even the walls of the station are falling. Everything in that little room is sharing nearly the same fall. And when everything falls together, there is no floor pressing up into your feet, no chair squeezing your body, no support force traveling through your bones. Your body is not being stopped from following gravity, so your body has almost nothing to report as weight. At first that feels wrong. I know it does. Because when we say falling, we usually imagine something dramatic and short. You drop a cup, it hits the ground. The story ends. But orbit is different. Orbit is falling with enough sideways motion that the ground keeps curving away beneath you. The station falls toward Earth. But Earth is round. So while the station drops, the surface bends away. It falls, and misses, falls again, and misses again. That endless missing is what we call an orbit. This is why I do not like the casual phrase, gravity is balanced by motion. It can make the whole thing sound as if gravity is being cancelled. As if some invisible force is pushing outward and fighting gravity equally from the other side. But that is not what is happening inside the station. Gravity is not gone, and it is not cancelled. Gravity is doing its job perfectly. It is bending the path. The station is not hovering because nature has switched gravity off. It is moving the way freely falling matter moves when nothing interrupts it. Once that clicks, the floating stops looking magical. The astronaut is not floating because gravity has disappeared. The astronaut is floating because there is no surface pushing upward through the body. No steady compression in the feet. No pressure in the spine saying, this way is down. The body is simply going along with the fall. And because everything nearby is going along with it too, the fall becomes silent from the inside. Now take that same idea and stretch it outward. A moon goes around a planet. A planet goes around a star. A star moves through a galaxy. And a galaxy moves inside larger gravitational structures. We are tempted to picture all of this as objects being dragged around by invisible ropes. But the cleaner picture is less dramatic and more powerful. They are following paths shaped by gravity. Same rule, bigger stage. If the parts of a system are carried along together, the system does not necessarily feel gravity as an internal strain. But now we have to be careful. Because there is one case where gravity does stop being silent. It does not show up as ordinary weight. It shows up as stretching, pulling, tearing. This happens when gravity is not the same from one side of an object to the other. Imagine falling feet first towards something enormously massive. Your feet are just a little closer to it than your head is. That means your feet are pulled a little more strongly than your head. On Earth, across the length of a human body, that difference is tiny, far too small to notice in daily life. But near something much denser and more massive, that small difference can become the whole story. Your feet are being asked to follow one path. Your head is being asked to follow another path. And your body is caught between them. That is the real heart of tidal gravity. It is not just gravity itself. It is the difference in gravity from one place to another. If gravity pulls every part of you almost equally, you fall smoothly. But if gravity pulls one part of you noticeably more than another part, then your body has to hold itself together against different motions in different places. And that is something matter can feel. Not as a neat definition in a textbook, but as stress, tension, strain. So the better sentence is not, "You can never feel gravity." That is too simple. The better sentence is this: you do not feel smooth, shared falling as weight. You feel resistance to falling, or you feel gravity changing across your body. Down here on Earth, that difference between your head and your feet is usually too small to matter. But near extreme objects, dense stars, black holes, places where gravity changes violently over short distances, that difference can become the main thing your body would know. This is why a person falling freely near Earth can feel weightless. Even though Earth's gravity is fully present, gravity is still pulling. But across the body, it is almost uniform. Your head and your feet are not being pulled differently enough for your nerves and bones to scream about it. So, for a short time, in a falling elevator, or inside an orbiting spacecraft, your body says something very simple. I am not being pressed. Therefore, I do not feel heavy. Deep space gives the same lesson in a quieter form. Far from large masses, gravity may be weak, and more importantly, it may be very smooth across the size of a spacecraft. The craft may drift for a long time without much gravitational stress inside it. Not because the universe has stopped having gravity, but because the differences from one side of the craft to the other are too small to matter. Everything is moving together. And when motion is shared cleanly enough, sensation almost disappears. Now the pattern is visible at many scales. A person falling near Earth, an astronaut drifting inside the station, a moon circling a planet circling a star. They are not separate mysteries. They are variations of the same idea. Gravity does not always announce itself by making something feel heavy. Most of the time, what you call weight is not gravity alone. It is gravity plus resistance. It is the ground interrupting the fall. It is matter pushing back against the path gravity would otherwise let you follow. And that changes the meaning of standing still. Because standing still feels so ordinary that we never suspect it of being strange. You stand on Earth, and you feel normal, stable, supported, at rest. But physically, something rather forceful is happening in a quiet way. Gravity is trying to carry you along a free path, and the ground refuses to let you go. The floor pushes up through your feet. Your bones push against one another. Your muscles make tiny corrections. Your body becomes a structure under compression. That compression is what you call weight. Now compare that with the astronaut. The astronaut looks strange to us because there is no familiar down. No floor claiming authority. No cup dropping to the same old place. But in another sense, the astronaut is doing the simpler thing. Not resisting. Not being pressed. Not being held away from a gravitational path. The astronaut is not escaping gravity. The astronaut is obeying it almost perfectly. That is the reversal worth keeping. On the ground, you feel weight not because you are freely following gravity, but because you are not allowed to follow it. In orbit, you feel weightless not because gravity has disappeared, but because nothing nearby is stopping you from falling with it. Once you understand that, familiar images change their meaning. Astronauts floating are not proof that gravity is absent. Planets orbiting are not proof that gravity has been balanced away. Falling objects are not doing something unnatural. They are showing us what matter does when nothing interrupts it. It follows the path available to it. It moves with the geometry around it. And it does not have to feel that motion from the inside. This matters for machines too. A spacecraft is not just a metal box peacefully floating through emptiness. It is a structure made of parts that must keep moving together. If one part is accelerated differently from another part, stress appears. If the gravitational field changes enough across the craft, stress appears. If engines fire from one end and push the whole machine forward, stress appears. Engineers have to think about where the push begins, where the metal bends, how forces travel through the frame, and whether every part of the spacecraft can keep up with every other part. So, the important question is not simply, is gravity present? Gravity is almost always present in some form. The better question is anything resisting the motion gravity gives you? And is gravity changing enough from one part of the object to another to create internal strain? Those are the things that turn silent gravitational motion into something measurable. Something structural. Something you can feel. That is why gravity feels so different from many other forces in ordinary life. A hand pushes you. A chair supports you. A wall stops you. These are contact forces. You feel them because matter is pressing on matter. But gravity does not need to press on your skin like a hand. It shapes the path your body wants to take, and only when that path is blocked, or when different parts of you are asked to follow different paths, does the feeling become obvious. So when you see an astronaut floating inside the station, do not think. There is no gravity there. Think instead. Everything in that room is falling together. The astronaut, the air, the tools, the camera, the walls of the station itself, all sharing nearly the same motion around Earth. No floor has stepped in to say stop. No surface is pushing upward through the body. So the body feels free. And when you stand on the ground tonight, maybe the ordinary feeling of weight will seem a little less ordinary. Your feet feel the floor not because standing still is the deepest natural state, but because the earth is holding you away from free fall. The pressure in your legs, the pull in your back, the simple sense of down, all of it comes from resistance, not from gravity speaking directly to your nerves. That is the final turn in the idea. Gravity is not always something you feel. Sometimes it is the thing you follow without feeling it at all. Sometimes the feeling comes only when something gets in the way. The ground, The floor. The frame of a spacecraft. The difference between one side of your body and the other. These are the things that turn gravity from silent motion into physical sensation. So the next time someone says astronauts float because there is no gravity in space, you can smile a little. Not because the simple answer is stupid, but because the real answer is more interesting. They float because gravity is still there. They float because they are falling with the station. They float because nothing is pushing back hard enough to make the body feel heavy. In a strange way, weightlessness is not the absence of gravity. It is what gravity feels like when you are finally allowed to follow it. Now stop for a second. Because this is the little trap in the whole question. You stand on the floor. Your feet feel pressure. Your knees carry you. Your back slowly complains if you stand there long enough. And the obvious sentence appears in your head. I am feeling gravity. It sounds perfectly reasonable. I mean, what else could it be? You are heavy. The floor is under you. Earth is below you. So the answer feels simple. But physics asks one of those annoying little questions that ruins the simple answer. Are you feeling gravity itself? Or are you feeling the floor stopping you from doing what gravity is trying to make you do? That sounds almost like a word game. But it is not. Imagine the floor suddenly vanished. Not slowly. Not politely. Just gone. Gravity would still be there. Earth would still be acting on you. Your body would still follow the path gravity gives it. But the pressure under your feet would disappear. The squeeze through your legs would disappear. That familiar heaviness in your bones would disappear. And that is the strange part. The thing you call weight was not gravity speaking directly to your nerves. It was the interruption. It was the floor pushing back. It was the world saying, no. You do not get to fall that way. Try to feel that picture for a moment. Your body wants to follow a falling path. The ground refuses. That refusal enters through your feet, moves up your ankles, climbs through your legs, reaches your hips, your spine, your shoulders, and your nerves report it as pressure, heaviness, weight. So the sensation is not gravity alone. It is gravity being blocked. It is motion trying to happen, and matter getting in the way. Now free fall makes the trick much easier to see. Not because gravity turns off. Please do not picture that. Gravity is still there. The difference is that the usual resistance has been removed. In free fall, your head, your chest, your stomach, your feet, all of you is falling together. No floor is pushing on one part of you while the rest of your body tries to continue downward. No chair is pressing into your back. No ground is sending stress up your bones. And without that stress, your body has almost nothing to report. This is why weightlessness feels so odd at first. It is not a new force arriving. It is an old pressure disappearing. You were so used to that pressure that you gave it a simple name. Weight. But take the support away. And suddenly the name stops matching the situation. In a falling elevator, in an aircraft following a falling arc, or inside a spacecraft orbiting Earth, the same thing is happening. You and the things around you are sharing the fall. A pen floats beside your hand not because Earth has forgotten the pen, but because the pen and your hand are falling together. Neither one needs to press hard against the other. So the ordinary signal of weight goes quiet. Here is where our everyday picture misleads us. We imagine gravity as an invisible hand pulling down on us. And for normal life, that picture is good enough. It gets you through walking, jumping, dropping a cup, catching a ball. But when you look more carefully, especially in Einstein's way of thinking, gravity is not best pictured as a little force pulling inside every part of your body. It is more like the shape of space-time, telling objects what path to follow. A falling object is not struggling against gravity. It is doing the natural thing. It is following the path available to it. And this flips the ordinary picture upside down. Floating in orbit is not the weird case. Standing still is the weird case. An astronaut inside a spacecraft is not floating because some anti-gravity machine is helping him. The spacecraft is still under Earth's gravity. It is falling all the time. It just has enough sideways speed that it keeps missing the ground. Inside it, the walls, the astronaut, the tools, the drops of water, all share nearly the same fall. So there is no strong push through the astronaut's feet saying, "You are heavy." But there is a catch, and it matters. You can feel something gravitational when gravity is not the same across your whole body. Suppose your feet are pulled a tiny bit differently from your head, or one side of you is pulled differently from the other. Then your body is no longer moving as one perfectly smooth piece. Tiny differences appear. A little stretching, a little squeezing, a little internal stress. This is the idea behind tidal effects. Uniform gravity gives your nerves almost nothing to hold on to. Changing gravity gives them a difference. And bodies are very good at noticing differences. So here is the clean answer. You cannot feel gravity directly because gravity acts on all of you together. When every part of your body follows the same gravitational motion, there is no argument inside you. No bone pushing hard against another bone. No pressure pattern for your nerves to translate into a feeling. You feel weight when something blocks that motion, or when gravity changes enough across your body to create stress. In ordinary life, the floor does the blocking. That is what you feel. And that tells us something very humbling about the body. Your senses are not designed to give you a perfect copy of reality. They give you useful signals. Signals that helped a creature survive on the surface of Earth, on solid ground, under constant support, with pressure always coming up through the feet. So of course weight feels basic. Of course it feels like gravity is something you directly experience. You have spent your whole life touching things that stop you from falling. Floors, chairs, beds, roads. The resistance has always been there. So your mind treats it as normal. But remove the support, and the story changes immediately. The feeling disappears. Gravity remains. That is the key. The physics did not go away. Only the sensation changed. So sensation and reality are not the same thing. Sensation is a filtered message. It depends on what your body is touching. What is pushing on it? What is stretching it? What is stopping it from moving freely? Now return to the original question. Why can you not feel gravity even though it never stops acting on you? Because your body does not report uniform falling motion as a direct feeling. It reports stress, pressure, resistance, distortion. Without those differences, there is no clear message for the body to read. Gravity can guide your motion every second and still remain almost silent to your nerves. Once you see that, even standing still starts to look strange. You are not simply resting there doing nothing. Your body would naturally follow a path shaped by Earth's gravity. But the ground is in the way. The floor pushes upward on you every moment. Not once, not occasionally, but continuously. That push travels through your feet and legs as stress, and your brain calls the result stability. But physics looks at the same situation and says, no, this is not passive. This is support. This is resistance. The floor is not just quietly sitting under you. It is forcing you away from the path you would otherwise take. That is why your feet feel pressure. That is why your legs get tired. That is why standing for a long time feels like work. Weight belongs not to gravity by itself, but to gravity being resisted by matter. So gravity is not absent when you feel nothing, and it is not felt in its pure form when you feel heavy. That is the reversal. The feeling of weight is not gravity announcing itself directly. It is the world interrupting your fall. It is the ground saying, you cannot continue along that path. And because that interruption happens through your body, you feel it as force. This is why gravity can guide planets, stars, galaxies, and your own body, while still being so quiet to direct sensation. It does not need to shout through your nerves. It shapes the motion itself. It bends paths, guides, orbits, decides how falling happens, and tells matter how to move through space-time. But unless something resists that motion, or unless the gravitational field changes across you, your body has no strong signal to feel. So the next time you stand on the ground and feel your own weight, try a different picture. Do not imagine that you are directly feeling gravity in its pure form. Imagine your body trying to follow its natural path through curved space-time, and the ground holding you away from that path. The pressure in your feet is the clue. The ache in your legs is the clue. The heaviness you feel is the clue. Not of gravity alone, but of resistance. And once that picture settles in, standing still no longer feels like nothing. It feels like being held, and set merely resting on earth. You are being supported against the motion you would naturally follow. Held above that path by the matter beneath you. Held in a condition that feels normal only because it has been normal your whole life. That is the quiet trick gravity plays on intuition. The thing that shapes your motion most deeply is not always the thing you feel most clearly. And the thing you feel most clearly, your weight, is not gravity itself. It is the interruption of the motion gravity would otherwise give you. I would rather have questions that cannot be answered than answers that cannot be questioned. Richard Feynman. Thank you for staying with this journey. And the next time your feet press against the floor, remember this small reversal. You are not feeling gravity in its pure form. You are feeling the world holding you back from the fall you never notice.